the three main factors. One of them is temperature related to aging, also rate of loading, and we talked about aging. Temperature, when you test the binder at different temperature today, without aging considered, you will see different results. If you test the asphalt binder at different rates of loading, you will get different answers. Okay, let's look at this first. Effect of temperatures on binders, asphalt binders response. What you're seeing here is a range of temperatures that you see in the field. Let's say it's in Fahrenheit, minus 20 Fahrenheit. I did see this once I was driving from Washington, D.C. to here on my dashboard 4 years ago. So the binders behave like a basketball. It's an elastic material at these temperatures. Actually, if you go even lower, then this ball becomes a glass. There's something called glass transition temperature, so it becomes like a glass, no longer an elastic material. But I don't want to get in there. So it becomes like literally a glass. If you drop it on the ground, it will split. And we do that in the lab, actually, just in case you're wondering. We put binder in liquid nitrogen to look into structure, and if you drop it, then it becomes a whole bunch of little pieces of glass. So I can show you that in the future if you're interested. Now, as the viscosity, I'm going to talk about viscosity in a minute. Let's talk about stiffness and viscosity. I'm sure you know what stiffness means. So stiffness goes down, and viscosity and stiffness are related directly. Stiffness divided by frequency is viscosity. I'm going to tell you about that. Stiffness divided by frequency of loading is viscosity. They are the same thing. So as the temperature goes up, then binder becomes like a honey, and as we go up, it becomes like water. The viscosity becomes water, and we want this. We want the binder to be like a water at the construction temperature so that we can mix it and work with it. Now, another important property is the speed of loading. At high speeds, let's say if you're driving on a highway 120 miles an hour, your binder is going to act as if it's a very stiff binder. If you apply a load that very slowly, then binder will act more like honey. So the same temperature we're talking about. So the speed of loading, this is called time effect or rate of time effect, time rate effect. So it reduces. So if you look at C, I'm going back and forth, back, temperature, time, temperature, time. There's something called, you're going to hear today also from others, there's something called, look at the curves. Do you see any change in the curves? I'm not changing. I'm only changing the x-axis. There's a reason for it. Time, yes. Yeah.
On the printout, the red rate of loading and temperature did not show up.
This one did not show up there?
Yeah, the rate of loading and temperature did not show up.
Oh, I see. Okay. So rate of loading or time, please put a note, time and temperature. There's something called time temperature superposition principle that we're going to talk today because we use that in Superpave binder design. Time temperature superposition. Time and temperature are interchangeable in the properties of the binder. They are interchangeable. So I'll talk about that later. Now let's go to scale 1. Let's go back to scale 1, which is the pavement structure. If I go to scale 1 and if you see this moving, by the way, this is actually a true simulation. We have a code called layered viscoelastic analysis, LAVA code that we developed years ago for Federal Highway Administration. So you have moving tire moving, and we are looking at the vertical strain at this point as the tire approaches. As you can see, the strain as it approaches slowly increases because the effect of tire is being felt here as it gets closer and closer, and then goes down. Now, I'm going to define, we define frequency approximately. This is not the most accurate, but if you look at this, 0.4 seconds, the total duration of pulse approximately is 0.4 seconds, and frequency definition is 1 over 0.4. 1 over seconds is your hertz, it's 2.5 hertz. So this is 2.5 hertz load. So this particular point feels 2.5 hertz of load. Now, if you have a faster load, let's say if you're going 80 miles an hour, so we were going, by the way, previously we were going 40 miles an hour. As I said, this is a true simulation. So 40 miles an hour, you see a 2.5 hertz frequency. If you're going 80 miles an hour, you see your pulse duration is much shorter. It's 0.2 seconds, and 1 over 0.2 seconds is 5 hertz. You can see when you double the speed of loading, you're really doubling the frequency of loading that this point in space or point at that pavement feels, okay? Speed and frequency. So all the tests that we run, it's based on frequency. We don't use speed. We just convert it, and we look at into approximate conversion from speed to frequency. So we are looking at 25 hertz, very high frequency, to 0.1 hertz. So if you look at the curve remained the same. So speed versus frequency is the same. What you're looking at is here, you have high frequency, short pulse load, low frequency, a longer pulse load. And at high frequencies, high stiffness, high frequency, high stiffness, low frequency, low stiffness. So you have your stiffness goes down with frequency. Okay. Now, another complicated, now the curve changed. Now, with aging, with time, we are talking about years now, not the time scale we're talking about in the lab. From 0 years to 20 years, you see, we know for sure that the binder ages. The binder is pretty much the only component in asphalt pavement changes the property. Aggregates don't change much unless you're using Michigan aggregates. Sorry, Dan.
Can you go to the previous slide, please?
Yes.
Yeah, frequency of loading did not show up either. I'll make a note of that.
Yeah, I should be avoiding this red next time. Frequency of loading.
Sorry for the interruption.
Yeah. Throughout the lectures today and tomorrow, if I pick on the Michigan aggregates, just excuse me, okay? And I'll tell you why in the afternoon, one of the days. Okay. Now, aging. So aging really means, we can talk about now, you have a fresh, nice, elastic material, let's say at a certain frequency, at the temperature, and the stiffness goes up, and stiffness, as the stiffness goes up, the stiffness doesn't just go up, it also causes binder to become brittle, more and more brittle. So increase in stiffness doesn't always mean brittleness, but in this case it does. The binder, as the stiffness becomes stiffer, binder becomes more brittle and more prone to fracture, not less flexible. So